Welcome to my talk, and thank you again, Elena, for a very wonderful introduction. I apologize if I go a little bit quick. I think one of the troubles with having a lot of time to prepare a lecture is that you try and squeeze in a whole lot of information that becomes packed with dense material, and it may seem a little bit intense, but hopefully that's also good. So why is reinforcement learning so exciting? Hopefully you're all coming here to find exactly that out. So to explain that, firstly, I have to say, what is reinforcement learning? And give you definitions. So let me give you sort of the hook. Imagine you're trying to get a helicopter to, pilot a helicopter. It's actually quite a complex operation. Just one part of this is consider the blade that's rotating around, and you have against that the torque. So you need to compensate for the torque by getting the tail rotor. Now, every time you change something, for example, you change the pitch of the blades, that means that you also need to try and increase the thrust, because if you make the blades drag more, you'll need to add more thrust to get the rotation still the same speed. But you'll also need to change the tail rotor thrust to try and compensate for the additional torque that's happening. So every little change is compensated by two other little changes. And that means that flying a helicopter is not simple. Therefore, this little video is quite surprising. It shows how reinforcement learning was used to really carefully and tightly control a model helicopter in flight and be able to come out of it really smoothly. So how do you do it? Well, the answer is reinforcement learning, but what is that? That it actually fits into an area of machine learning that runs alongside supervised learning and alongside unsupervised learning. And essentially all of them have to do with having data, maybe slightly different sorts of data. Supervised learning is going to be more being able to say, this is a picture of a cat. Unsupervised learning might be able to relate, well, you're buying lots of beer, so that means you may also be at the same time going for nappies. Whereas reinforcement learning is sort of basically more of a trial and error approach, but also acting on a sequential task that may see a successful outcome in a series of trials. So basically something that happens over a period of time. Okay, so let's go and make some definitions about this. So the first thing I need to define is the term policy, and you'll probably hear me say this a lot and wonder what it is. So what is it? A policy is really just a mapping of the state you're in, the situation, to some action. So every time you're in a situation, you need to know, what do I do? How do I act in this position? So your table, if you like, of situation to action is called a policy. The next thing you need to know is, well, how much reward you get for doing that action in that state. And this is an immediate thing. So sometimes you get no reward for a long period of time, and then you'll get a really big reward. But the reward function just tells you how well you're going to do immediately with this particular state and this particular action coming from it. For the long term, the term is value function, essentially the value of, or the long-term discounted reward. So as you can imagine, if you have a long episode and you take a series of rewards over all those episodes, eventually you're going to build up a total reward. You might be able to win a chess game, for example, or you might not win the chess game. And you can get an expectation of your reward at the current time through a value function. Now note, the thing about the value function is it's peculiar or particular to the policy. You change the policy and the value function also changes. Okay, so the final thing, possibly the most important thing to remember for this talk, is the idea of a model. Essentially, it's how the environment responds to the agent, as in or could be, when I say agent here, you could also say robot. It may not be a robot, it may be a software agent, but let's just think of it as a robot. So in this case, the helicopter, for example, is the physics of what happens when you apply additional thrust to the rotors, or change the pitch angle, or change the amount of thrust to the tail rotor. Those sorts of things have a physical effect in the real environment, but when we want to simulate them, deal with them inside a computer, we need to know how that plays out from time step to time step, the dynamics of it. And further, a couple of small definitions, the idea of states, that's the individual situations, and actions, what you can do in each particular situation. Right. So this example is an example problem. It's actually from Russell and Norvig, a very famous AI book. And what's going on here? Well, we have a grid world. Essentially, our robot can move around the grid. It moves precisely one unit or in any particular direction. However, there's some slight problems with this environment. In particular, sorry, let me go back. Finding how to pause the video. Okay, so in particular, we can, if we try and move north from, say, this 1-1 position, it might actually move us north with a 0.8 probability, 80% chance, but actually it might get knocked to the left or the right where it's trying to move with 10% chance each. So that makes this problem a little bit harder, not terribly hard, but a little bit harder. And that forms our model, right? Our model of our environment. We also have a reward function, which is indicated by these +1s and -1s, the green +1 and the red -1. The +1 obviously is where you want to get to. The -1 is the place you want to avoid. If you get either here or there, then that means that you've come to the end of the episode, that everything finishes at that point. In any other point, you also have a -0.04 reward. That just means don't take too long, don't dawdle, don't just stick around in the same spot forever. Okay, I can just explain how the model works a little bit better by taking that 1-1 point and sort of annotating it with, well, if we try to go north, we try to go east and so forth, what happens? Well, we know that 0.8 probabilities, we actually go north, but with 0.1 probability, we knock into a wall, right? So we end up in the same position we were, and so forth. And we can annotate all the points like that. Okay, so given that, and starting with a uniform random probability, we can gradually get through to progressively improved policies. And these numbers are the value function for each of these states based on whatever that policy was. Okay, and if I just rewind a little bit, we can see what policy we ended up with. Okay, there was the optimal value, and then this is the optimal policy. For this problem, this is the best way of moving. If we change the reward function, it changes what happens. So for example, we could change this -1 to a -10, and that gives us a different value function naturally. And it also means we might end up with different policy. And indeed, that's exactly what happens. And here's the optimal policy for that. And you can see that it's really trying to get away from this in this bottom right-hand corner, really trying to get away from this -10, which is considered very bad. Okay, so just another example, just get you used to the idea of what a state is, what an action is. Here we've got states that are made up of the pole angle, the angular momentum, the cart position, and the cart's velocity. right, in which direction. And we can act by trying to push the cart to the left or to the right. We also get a +1 reward every time step that we keep the pole upright so that it doesn't fall over. This is quite hard as a problem, because now in terms of the space of possible states, it's continuous. Like there's a sort of an infinite number of possible pole angles. So that sort of makes it a bit harder. Here's another example. Maybe we want to play soccer with robots or football with robots. So the states are to do with where are you on the field? Where are the other players? Where's the ball? Maybe which direction am I turning? And then the actions are to do with, maybe turning, running, passing, shooting, tackling. And then your reward function is to do with, do I get a win, a 1 for a win, a 0 for a draw, and -1 for a loss, and maybe just 0 any other time. Of course, that's going to make it quite hard. And you could say, okay, well, maybe I just simplify that problem and say, well, just give me 1 for each goal I score. But that'll end up with a different optimal policy. You'll end up playing differently if you try and do things like that. Okay, so let me just give you some background about reinforcement learning. I think it's got quite a nice history to it. So these cats are sort of emulating that Pavlov dog idea, which was about the turn of the 20th century, 1897, I think it was. He did his experiments on dogs. And the key thing was that he got was that the idea that the experience of some reward, such as food, reinforces an action. In his case, Pavlov's dog was salivating. In this case, this one, it's the cats are just working out to ring the bell. Okay, by 1950s, cyberneticists had come across the idea that maybe the brain, animal behavior, could be summarized with relatively simple rules. And this is really a really exciting video to find, because I knew about this work for ages, but the video seemed lost, but recently came across it. So what he's showing here is a robot that is turning towards the light, and it's got a photoreceptor. When it sees the light, it moves forward, moves towards the light. It also has on its chassis a bump detector. So when it feels some bump, then it just moves in a random motion, trying to get away. And the important idea here was that it's able to do quite sophisticated seeming behaviors with actually very little information, very little logic to it. That idea, by the way, was taken up really later on and became sort of core to robotics. Now, by 1957, Richard Bellman had devised the concept of dynamic programming, which is really a core concept in control theory. And in essence, if I just rewind to the start of this, you'll see this, this equation here is really just saying that the long-term reward is made up of, well, the next state short-term reward plus the discounted next state after that's reward, plus double discounted next state after that's for reward, and so forth, right? If we have a bank account, we're familiar with the idea. But the point he made was that, look, you can do this. You can take out at least one of those gammas, and actually, well, that just looks like this. So we can simplify the whole equation to saying that the discounted long-term reward is next state reward plus discounted of the long-term next state reward. And that means that computation as well can be short-circuited somewhat. And that's the basis of dynamic programming. Now, by the time 1983 came along, these wonderful guys, Bartow, Sutton, and Anderson, really founding fathers of reinforcement learning in many ways, came up with the actor-critic architecture. And essentially what this is saying is, Well, you see some reward in your environment, and maybe it's the reward you expect, maybe it's less reward, maybe it's more reward. That difference is called the TD error, or temporal difference error. And you use that not only to update your value function, your estimate of how much value you actually receive in that state, but also to change your policy. And by doing these at the same time, this architecture is called the actor critic. You've got an actor, somebody acting, and also a critic, someone who's saying how good that is. Okay, so that was a heuristic approach, but really, interestingly, some seminal work of Watkins, he came up with queuing, which ties both Richard Bellman's ideas of dynamic programming together with this idea of reinforcement learning, or sort of heuristically updating your value. And in this case, he specifically broke it down into not just the value of the state, but the value of taking a particular action in that state. And that's an enormously important idea in reinforcement learning. Now, the other aspect of this that I need to point out is that this is a learning algorithm. And that means that it doesn't start off, it doesn't write down a strict equation, this is what it is. It says, we'll have an estimate, and then we'll gradually get closer to that estimate. That's why there's a new and old happening here. So this was probably the first important reinforcement learning algorithm. And one of the particularly nice things is that it's proven to converge. Okay, so in terms of successes, Tesaro produced this wonderful backgammon playing game in 1992, thereabouts. And the key thing about this game, well, backgammon, as you know, game of chance, has quite a few states. There's many possible ways of playing the game. The thing that's really interesting about this is that it sort of completely solved this game. If backgammon players now want to find out how to play in a particular position, they could use TD gammon to find out what the best play is. Now, if computer science stole ideas from neurosciences with cats and small tin robots, then interestingly enough, neuroscientists are now stealing some of those ideas back. So by 1994, there were papers coming out that were saying, hey, look, there are links that the ideas that are happening in reinforcement learning, particularly TD learning, temporal difference learning, well, that's actually the same basic set of equations that we're seeing when we're modeling what's happening in the brain. My own work finished around about 2002, and it was to do with basically around that robot football that you saw earlier, although maybe a little bit previous version of it. And I was trying to solve this problem. Ordinarily, when you get a two-wheeled robot and you try and steer it into a target point, which is sort of illustrated by this green circle, you get this effect. Essentially, it has to start off at this red square, and then it will try and first slow down so that it's not moving quite so fast, and then turn towards the target location. Sometimes it will turn a little bit too fast and flip right round, and so that it goes too far. And you can see it sort of ending up facing completely the wrong direction. And eventually it'll come back and accelerate towards the target and get to the point. So it's slow and maybe not really what you wanted. So how do you improve it? Well, here's what reinforcement learning can do. And for me, this was particularly exciting because I was also, it's a small enough problem, but I was also able to solve it using depth-first search. And that means I can know absolutely that this corresponded to pretty much exactly the optimal solution. Okay, so I also did a number of other sort of stunts, if you like. One of them is ball dribbling, and the hand-coded algorithm was doing this sort of thing. It would try and turn with the ball, but the ball would sort of drift off to one side. What do you do about that? Well, you can see that the reinforcement learning algorithm managed to learn to be much more careful, but also to respond to the ball drifting out and to actually change its behavior. So shortly after that, very excitingly, we have the helicopter from Andrew and Peter Ebiel as part of Stanford helicopter project. And the thing that's amazing about this, particularly, is to do actually with the way they did simulation. So all these stunts, before they put them on the helicopter, they've learned them with reinforcement learning in simulation. So initially, when they were trying to simulate the robot, the helicopter, I should say, they used sort of physics-based differential equations and didn't work. And didn't work for two reasons. Firstly, it's too slow. And secondly, it's not really accurate. The real helicopter didn't correspond actually to the to those physics-based equations. Now, some people would say, well, just tune it. But what they did instead was they took data from the helicopter and they interpolated from this experience and created a simulator essentially that was based on this interpolated experience. And that produces the stunts that you're seeing here. And I think it's really quite amazing work. So you may have heard of deep reinforcement learning and be wondering what that is in comparison. And the main thing about deep reinforcement learning was that firstly, to be able to take not just the internals of what the Atari game is doing here and be able thus to work out what the right answer is, but just to take the pixel values. So this reinforcement learning agent is learning based on just the pixel values. It sees the pixel values and then it knows how to move that little bat down the bottom. Now, it's very interesting that actually not long into the process of learning, it works out what everyone pretty much who's gone through that area knows the best strategy is to get the ball behind so that it does most of your work without coming back and being difficult to bat back. And I think this is really amazing because it seems like deep strategies would be not available to such an approach, but actually they are. So with the AlphaGo, it's probably the most, one of the incredibly exciting innovations of recent years. And basically they've played successfully against Lee Sedol, beat him 5-0. And the reason why it's really exciting is because previously computer scientists just thought Go was completely impossible for computers to solve. At each point in the game, you've got this huge branching factor. That means that to explore the problem to any depth, then you need to actually explore a huge space, and much larger, many, many times larger, in the orders of magnitude larger than chess. So the other point about AlphaGo is that once they've trained it, they just put it into a laptop and it will run. They can take the laptop to the competition and play it that way. It doesn't require, the policy doesn't require a lot of computation. It's been learnt and that's it. It doesn't need to be altered. You can learn it more, but it doesn't need to be altered for it to be used. Okay, let's go back to robots for a second. We all love robots. So these guys are doing some amazing work to do with simulating first and then trying out on the real robot. And what they noticed was something interesting. Basically, the simulator wasn't quite accurate enough. And that meant that the robot fell over when they tried it. They used an improved simulator and that led to this wonderful running gait. And as you can see, this works really nicely on the real robot. So the final bit of historical information I'd like to tell you about is this wonderful work by OpenAI to get a single-handed robot to solve a Rubik's Cube. And this is really impressive in terms of its what they've done here. But what they probably you can't see on the screen is that to do this, they were doing many trials in simulation. And in particular, the problem that they had with simulation is that you really need somehow a perfect simulator, and you can't really obtain it. So what do you do? Well, they actually used some randomization embedded into this simulation to make their behaviors, the things that they were learning, really robust to all sorts of different physical environments. So even small changes in the physical environment would be robust too. Okay, let me talk to you about some of the key challenges for reinforcement learning, particularly applying reinforcement learning to the real world. It's like to start with the common framework problem, right? How do we make sure we have a common framework? So this has really been taken forward, and great advances have been made by OpenAI in particular. OpenAI Gym has provided us with some really good framework stuff and algorithms that run particular learning algorithms, particular variants. I think the other part of the problem is not just the coding part, but also the problem definition. You know, if we're talking about so robot soccer or the hand gripping problem, we want to have a standard way of stating what the problem is, so that everyone sort of can compete on an even level, on a level playing field. The simulation environment is really key to this issue. And sorry, I just lost my train of thought there for a second. So what I'd like to say is really that the coding simple simulation environments like the game of chess or Go, it's easy, the results are fast, and there's no question that your simulator is doing the right thing. But when you actually take it for sort of more physical problems, it's quite clear that bugs in the simulator can lead to very poor control behavior. And we've seen this in a couple of cases. And the thing is that if you're simulating some physical system like a helicopter, maybe it also involves solving some complex differential equations. So what do we do? Well, I hope to give you some answers to that in a second. The third thing I want to tell you about as being sort of a key challenge for reinforcement learning is having sufficient data. And I think that it's really well accepted, Andrew has given a talk about this actually, about, you know, neural networks need a lot of data, reinforcement learning needs even more. And in particular, it's important that we can simulate our environments really successfully. Now, a lot of data collection is occurring today privately, and I think that, you know, as scientists, we should be encouraging as much as possible collection of open data so that we can sort of try and overcome some of these difficulties. And then the fourth thing, a final thing that I want to talk about in terms of challenges is the human element. And what I think this video really nicely portrays is that even though human beings are complex creatures, that there are some simple rules that help you get to the heart of what's going on. And the simple rules here are to do with the fact that when you're walking, that you tend to match pace with the person in front, that you tend to actually walk behind people to have an easier passage. And, you know, everything else can really be derived from that. So this actually often looks like a simulation, but it's real people. I think that's quite a nice example. Okay, so now I want to switch and talk to you a bit more about my own work. And it's to do with electric vehicle comfort control and applying reinforcement learning to that problem. So why do it at all? You know, why is this an issue? Well, the first thing is that electric vehicles have quite limited range. If you drive an electric vehicle, I personally have an electric vehicle. Quite recently, I've got one. I love it, but the thing is that you have to be really careful about how far you're going to go. And in winter, that's going to change because it's cold. And in summer, it's going to change because it's too hot. Why? Because the air conditioning system is taking a lot of power. Now, add to that the issue that I really perceive that the industry for cars has really evolved to develop individual components. So they don't give you a holistic comfort system. They give you a sort of very componentized comfort system. And that's because it's easy for them to do it that way. It's not necessarily because it's the best thing that they could be doing. Now, the question is, could we have a holistic view? I think this is something that maybe we really need to think about. And then the final thing that I want to mention as sort of a motivating aspect of this work is that in the built environment, it's become clear as we changed how we thought about our heating models, thermal comfort models for human beings, that actually the way people react to their thermal environment does not require the air conditioning to give perfectly 21 degrees all the time. And what does that mean? Well, that means that actually you can have buildings like this wonderful library that we have at Coventry that has natural ventilation. You can see those stacks up the top. And this building is actually 50% less energy consuming than the equivalent air-conditioned building. So maybe the same things could be applied to cars. So I've been working on this problem for a while, and I started working with Jaguar Land Rover some number of years ago now. And I think that the interesting thing that I really saw at the time was that they weren't really looking at this as a potential thing to work on. They didn't see it as something that they were just happy to go along with the same old approach. And I think that it was really sort of striking when I was working with them. But I got the opportunity more recently to join a Horizon 2020 project, and I'm thankful for the other partners in this project for their assistance in driving really this work forward, and particularly in the approach of thinking about the problem much more holistically. So let's just go and tell you more about my formulation of this climate control problem, or comfort control problem, as you might call it, and particularly as how it would be solved as a reinforcement learning problem. So I've talked to you about policies and states and reward functions, and now we can put them in terms of this particular problem. So we have over the left-hand side here a cabin model. This is actually made up of really three distinct parts. Firstly, there's the air conditioning system, the HVAC, maybe the heated seats as well. Secondly, there's the thermal environment of the cabin, or the air in the environment, the chairs. And then thirdly, there's the human being involved, how they react to how they perceive their thermal environment. Okay, taken together, these things give us an idea of the state of the system, right? How that system is going in terms of its state. And also, we get a reward function out of that. And particularly, the reward function consists of three distinct parts. So the first part is, well, how much energy we're using. We want to minimize the energy. So energy is a negative element of the reward. Then the second part is how much comfort are we providing? And particularly, we want to be able to say, are we actually in a comfortable situation or not? And if we're not comfortable, then it's sort of like a negative one, if you like. And then thirdly, we want to be safe. The car windscreen needs to be demisted. And if it's currently misted, we need to be trying to act to try and avoid that. So that is then fed into our learning agent, who can then do control actions, things like adjust the thermal set points, adjust the seat heating, turn on fans higher, all those sorts of things that we know how to do. And then the final result is we end up with a policy out the end. And that's a policy that is essentially like a lookup table. So it's easy to code in a way that can be ported into the ECU, the engine control unit, internally to the car. So that work of describing how that works produced a patent in my name and in one of my students' names, and also in one of the Jaguar Land Rover people's names. So now we've got the issue, but I want to just focus on one particular aspect, that thermal cabin model. Now, there are many things to solve in the whole thing, but let's just focus on one aspect so that we can dive deep a little bit. The past work, my past work really, was worked out that it takes about 8 years of simulated experience to learn a good comfort controller. Now, you can use what's called CFD, computational fluid dynamic models, to work out what the temperature is at each part in the cabin. However, it takes a long time to simulate even a single second, maybe about 10 minutes, maybe even more than 10 minutes, depending on the problem. Now, you can have simpler models, so physics-based models, which are based on sort of just simulating really to 1 or 2 points in the cabin, but then they still take quite a long time to compute, maybe about a second per each simulation second. So what do? Well, the first thing is gather data. Now, how do we get the data? We need to put the car into a climatic wind tunnel. That's an environment where we can flow air over it. We can also change the temperature. And we also need to instrument the cabin, so we know the temperatures and mean radiant temperatures and airflows at all sorts of points within the cabin. And then we are set to do some acceleration of the cabin model. And the idea here is that it's really possible to learn the cabin model from data. Essentially, I'm saying, let's formulate it as an equation like this. We have our current state and our past states going backwards, and we just want to predict the next state, right? We also have these U's, which are the control actions. Now, theta stands for a vector, say maybe in a neural network or linear regression parameters. And the point is that such a function, that function f theta, is going to be much faster to compute than a CFD model, many times. So would a linear model work? So that's the question, right? And maybe we can get some intuition about whether or not that's true by doing this, starting from a simplified view of this, how the thermal model works. So very simple thermal models look like this. We have this dy dt differential term being equal to, and then the temperature, which is y, minus the external temperature, say, all times a coefficient, and basically tells you how the temperature will change over time. Now, that's sort of quite complicated to solve, and maybe you end up with something that looks like an exponential. But actually, you can approximate that by an approach called Euler approximation. And that leaves you with something that looks like this. And then we eventually get down to an equation that looks like this, which interestingly is linear. So basically saying this is sort of a constant, this is sort of a constant, and that means that we're linear as a function. So yes, it actually makes sense to think of the possibility of using a linear model. When we try it out, this is what we get. We get the pairs of lines here are the simulated and real values. So for example, here is the top pink sort of value is the simulated, the real head temperature, and the little blue line underneath is the simulated head temperature. Now this is maybe, that doesn't look terribly surprising, but let me tell you that the only thing that this simulator knew was the starting state. And it was able to simulate over many hours and still end up with pretty much the correct values after all this time. So that in itself is quite surprising. So the other thing that's really nice here is that this is distinguished between the head, the torso, and the foot really clearly, and shown how those the natural buoyancy of hot air rising in the cabin has actually worked to change those temperatures over time. Finally, it's fast. So we could simulate a year of simulated time in 3 minutes on a laptop computer. What do we expect from this using reinforcement learning? Well, these CM variants over here are a commercial controller for an HVAC produced by a company I can't name, but they were able to give us the details, and we were able to simulate that controller. And you can see actually that the control performance was really poor, and it didn't get very good comfort, and it used a lot of energy doing it. And in comparison, our learned controller, which is illustrated by this black line going along here, was able to do much better. The reason why it's a line and not a single point is because we tried different weights of energy versus comfort. So we can either have something that produces a really efficient down here energy, very little energy, but maybe not so great comfort, to something that is actually the best comfort that we can achieve, but still uses a little bit more energy than some of the other methods. Okay, so I just want to conclude and say thank you very much for listening. I think reinforcement learning is a really exciting domain. It's surprising in many ways it hasn't made bigger inroads into real-world systems. I think that the main reason for that are just to do with some of those roadblocks, lack of data, and maybe some safety fears. But I think the thing that I want you to really take away from this talk is that reinforcement learning is about optimizing things. And optimizing is not really just making something better, it's making it as good as it can be. And I think that this idea is quite important and the basis of really revolutionizing the way we think about both robotics and even software. Thank you so much for listening to the talk and your attention, and I open for questions.
Thank you, James. Well, we have a first question coming. That's from Aaron. Aaron is a Coventry University alumni. He congratulates you on the presentation, which I really think it was extraordinary. Although I heard it many times before, it was the best of all. His question is, does reinforcement learning mainly benefit the physical realm in computing, or possibly other studies and disciplines as well?
So I think it's really surprising how many areas can be affected by this problem formulation. Reinforcement learning is sort of a stance. It's a way of looking at a problem. And you obviously have to be careful that you're not just saying, okay, well, every problem is a nail and I've got to walk around with my hammer hitting it. But I think on the other hand, it's actually quite revealing to look at other disciplines, areas of concern, and try and say, well, could this be a reinforcement learning problem? So I think it's something that needs to be asked. That's a question that needs to be asked. So yes. Have I answered the question? I'm not too sure I have.
Well, that's up to Aaron to tell us. I think it was a comprehensive answer. I would very much believe that reinforcement learning would make its way because of its fantastic optimization capacity and capability. And I think that power is less understood today than it may be in the near future. Other questions?
I'm really hoping to get at least some other questions, but I'll be happy with one, if that's all I get.
Well, I have a few, and I'm going to just ask one. Maybe I'll get a different answer than the usual one. What's next?
What's next for reinforcement learning, or for me?
For you.
For me. So I think there are definitely lots of open bits of work that I really want to address. and particularly, I want to make sure that this project of getting the comfort control into the car succeeds and happens and is working, and all the issues around it are resolved. But I think that what's particularly been interesting to me over recent times is the human element, and I think that this is deserving of our attention. And I don't think many people are really looking at this issue. How do we deal with the human element in a reinforcement learning problem, and how do we simulate that human element? And then what are the ethics associated with doing that? I mean, that's it seems like quite a dramatic thing. You're going to simulate humans, and maybe there's some strong questions that the audience will have about that. But I think Manus had a question, but I didn't quite see the text.
Yes. Okay, so Manus is asking, how do we know whether we know enough about the environment in order to apply RL?
Oh, it's such a good question. So I think one of the interesting things about reinforcement learning, I didn't really talk about in my talk, but is that it sort of assumes that you have a fully observable environment, that you can actually sort of see everything. Now, in practice, that assumption can be weakened and flexed, right? But so that's usually one of the things that people think about. Can we actually fully see the state of our system? And then I think that in terms of if we have an accurate simulator, the question is it accurate enough to give us a policy that actually works well? And I think that should be the first question. And in very many cases, I think that there's an iterative approach that needs to occur, where you say, well, we'll try using the best simulator that we have that's sufficiently fast, that we'll see what policy we get out. And then we'll go and say, okay, well, now that we've identified that there are problems, very much like those walking robots, let's go and try and fix those problems and then come back into improving the simulation and go round again. So I think there's an iterative development cycle that can happen there.
Thank you, James. Are there more questions for James? Well, if not, thank you very much. Oh, there is one. There is one has come through. That's from Vasile. You combine RL with fuzzy techniques in your car environment control. It is interesting. I guess this is because you could not quantify the driver comfort well. I'm not sure I understood the question, but Vasile is welcome to verbalize it if you want.
Yeah, so you noticed that we had fuzzy control techniques, and we didn't combine them with RL. What happening there is we said, well, fuzzy is another possible option. So let's see how that works. So we just had a control that worked through fuzzy. We had a control that worked through more sort of traditional approaches. And we also had the commercial control. And we tried all of them, and they produced a massive points on that graph. And reinforcement learning was quite well separated from all of them. There wasn't any reinforcement learning in that part. And the question about how do we quantify the human aspect, well, we used existing thermal comfort models. Now, the question might be asked, are they correct models? And I think that's very much an important question. It comes back to this issue of the simulation loop, that the more that we probe this issue of, what would the computer do if given this type of model, what policy would it end up with? And we can start to see where are the flaws in the simulation.
Thank you. Said.
Thank you very much, James. It was a very nice presentation. James, I wanted to ask, well, I have more than one question, to be honest, but I don't want to waste your time and other people. Let's just start one by one, and then you stop me. First of all, I do remember reinforcement learning, Q learning that you described. Another algorithm related to Q learning, it was MaxQ, I remember. And I do remember its application in robotics, promoted at MIT by Professor Brooks, and also software agent by Woodbridge and Professor Clark at Imperial College, and Woodbridge at Cambridge, I think. However, now I thought, to be honest, I thought that reinforcement learning has not been so successful, and that's why it's not been so promoted. But now, when I listen to what you said, so I came to this question: why it hasn't been really explored over, I mean, 15 years since I knew it?
Yeah,
I wonder.
it's a good question, and I really want to know the answer too. So I can't pretend to have the full answer, but I think that part of the thing is that actually working in this area is quite hard. It requires, you know, when you have a system that is trying to control something, if you haven't done something right, it'll all fall horribly wrong. And I think that that's making it very much more difficult for people to publish their work in this area, that they've had a lot of sort of not quite so great successes. Perhaps their simulation wasn't right. Perhaps they chose the wrong reward function. But I think the thing that was surprising to me was, you know, when I went back and had, you know, did some sort of literature search as part of producing this talk, you know, actually how much work there is out there. And really, it is a very vibrant field at the moment. And there are a lot of researchers really actively working. I think the answer to the question, the other sort of question is, why haven't companies taken it on? I think you're going to start to see that change relatively soon. And I think that people, for example, are using it as sort of business logic methods. You know, they simulate their business effectively, and they use it as a solver for their business. And there are companies out there now that do that. Although, to be honest, I can't remember who they are, but I've seen them. I think we have some other questions.
Yes, we do.
Chat.
We have one from Heather, who would be interested to hear more about your views on ethics of RL, particularly the human aspect.
Right. Well, I think there's two parts to that. I think obviously we need to be careful of ethics in any part of science. It's not just reinforcement learning. Any part of science we need to be careful. And I think that what's interesting to me is how much reinforcement learning researchers are focused on safety of AI. And I think that's partly because the lay public tend to see videos of these robots doing clever things, and they instantly think, well, this is Terminator, you know, I'm going to sell all my things and go and live in the outback because that's the only way to escape these terrible robots. And I think that sort of sensitivity maybe has caused them to be extra careful. Now, when you look at something like Boston Dynamics, who are basically funded by the military, they're producing military robots, which, by the way, don't use any reinforcement learning. Probably one of the reasons why they're not using reinforcement learning is that they want to be absolutely sure of what that thing has learned, what it's actually going to do at any particular point in time. Now, it's actually a little bit hard to say in terms of ethics, you know, this relative safety. And I think this is one of those balancing things that we have to think about a bit more. But I don't know if I've quite answered the question. I think it's a really interesting discussion to have, but I'm aware that there are other questions. I'd better shut up.
So we've got one from Kojo. Would you be better off using model-free RL if the environment is not fully observable?
Yeah, so the fully observable aspect is really to do with whether or not your algorithm will converge to the optimal solution. And, you know, it's proven that it will if you have a fully observable environment. Can you work in an environment which doesn't have a full observability? I mean, I think just a sort of simple mind experiment, a thought experiment can help think about that issue. Imagine you have a robot that is just got a camera that's facing a particular way, like the robots on that soccer pitch, the football field. It can see sometimes an orange ball, but what if it can't see any ball at all? What does it do? And I think that deciding how to behave in that case optimally is quite hard. However, you know, you can sort of do you sort of know that you have to turn, and that turning is going to be the right answer. And that's one of the reasons why reinforcement learning will sort of find something that's actually pretty good. Will it be the optimal answer? Not completely clear. Formulating it as a partially observable Markov decision process, on the other hand, will definitely give you the right answer. Another possible way of doing it is to have a map of the field to keep track of where the ball last was. Maybe have a probability distribution over possible places the ball could be, and then work from that. And you can sort of say, okay, well, I think the ball might be over to my right shoulder. That way I'll turn that way. And then that's a way of dealing it. The model-free aspect is not necessarily helping with that, by the way. It's a slightly different issue, but I'm happy to discuss with you later.
So I think at the time, we are over time. Quite amazingly, we had a small but very interested group of people joining us tonight, and I can see from the chat that there are conversations that you've started, colleagues, with James, that needs continuing. So maybe a good debate is in order on the various aspects that have remained unanswered from the talk today. And I'm sure that we can organize one in our Center for Data Science if you would lend yourself to that, and we will definitely involve Yuri to come and join us, and the colleagues that have participated in the chat. But in the meantime, I'd like to thank you for a really delightful evening, James. You had great competition with the sunshine out there, and still you made it so very well. So well done, and thank you for a good talk on behalf of everyone attending.
Thank you.
Good night, everyone.
And good night.